Welcome, everyone. This is going to be a set of lectures on prerequisites for the class Foundations of Deep Learning. Let me start by explaining what I will be discussing in this set of lectures. So first, we're going to review relatively simple things like what is a vector, what is a matrix, various notations as well. Then I will move on to explaining also the things like the span of a set of vectors, what is a matrix multiplication, what is a matrix inverse. So these are concepts that I expect you to know. I will briefly review them. Then we'll go into chapter 2, so which is going to be on vector spaces. So we will see what is the definition of a vector space, what is the definition of a norm. I'll discuss also the Cauchy-Schwarz inequality, as actually this is something that we'll be using from time to time. Then I move on to a review of functions, more specifically concepts such as derivatives, the concept of continuity, Taylor's theorem, which allows us to expand a function on a point. And finally, we'll discuss a little bit more advanced concepts of linear algebra, things such as eigenvalues, singular values, and SVD decomposition. So let me get started with section 1. And as I said, so let's review first what is a vector. So more specifically, what is a column vector? So a column vector is simply a d by 1 dimensional array. So this is represented here. You have a vector and you have entries x1 up to xd, right? So we have d entries. And this is here represented as a column of the elements. We can obtain a row vector by actually transposing this vector here. And so, of course, you just get a representation like this, right? So now the elements here on a single row. So we have one row and we have here d columns. And this transpose operation, we denote it with this t here. So you would write it in this way, essentially, x over upper script t. All right. And what can we do with vectors? Well, we can multiply them using the notion of an inner product. So you have two vectors, u and v, which belong to Rd, right? So here again, Rd is a Euclidean space with d dimensions. And the inner product is something that we denote in this way, right? So we have u transpose v. And this is simply a sum. So you sum over all the elements of the vector. So you have a sum here from 1 to d. And you sum over all the elements, so you do ui times vi. Then there's another concept that we have to review, which is the concept of a span of a set of vectors. The span of a set of vectors is the set of all possible linear combinations of these vectors. So mathematically, it works in this way. You have a set of vectors, which are here denoted by v1 up to vk. So we have k of these vectors in this vector space v, and I will be discussing the notion of vector space in more details later. For now, you can just take this as a set of k vectors. And we are talking about the span of these vectors in the following way. So we write span of these k vectors here. And what we do is that we'll take ck, let me highlight this. So we take ck scalar numbers, and we take linear combinations. So you see here, I've seen one up to ck. We take linear combinations of these vectors, okay? And this is a set, right? So here, again, notation, remember this means set, right? And this means we're looking at all the values of all the values for the C1, C2, and CK. Okay, let's look at it on a picture. So here, let me give you an example in 2 dimensions. So we have, let's say, just x and y. So this is, let me write it here. This is an example in R2, right? So d, the dimension, is equal to 2. And so we have 2 vectors. We have v1 here, whose coordinate is -3, 2. Okay, so -3 here and 2 here. And then we have the red vector 2, 3, which is shown here. And what we are going to do is we're going to take linear combinations of these 2 vectors. Let's assume for now that in this purple area, what we are doing is that we are looking at combinations C1 and C2, which are in the interval here 0 to 1. And if you do this operation I mentioned before, right? So going back here, you take C1, C2 in, instead of R, you just do it in the interval 0, 1, you will get this parallelogram area here. So what does it mean? That means if I take any combination of V1 and V2 with these coefficients here, I get a vector that is inside this blue parallelogram. Okay, so for instance, you could take, so first of all, just to say you take C1 and C2 to 0, you get just the 0 vector here. So this is indeed inside this blue parallelogram. If you take C1 and C2 to be 1, so you get this point here, right? Because that means you're adding essentially V1 to V2, so you get to this point. So that means you get this vector here, this one, and so on, right? So you can take different combinations. So here I give you another example. For instance, you take the C1 equals 0.5 and C2 equal 1. And you can write this linear combination in this way. So you can put these two vectors, V1 and V2, here in this matrix form. So you get essentially, if this is a vector C that consists of C1 and C2, you just get V times C. And you can, of course, just write it in this way, right? So this means that you take 0.5 of the first column. Let me highlight this in different colors. So here we have the first column, which is a V1 vector, just here. We take 0.5 of the V1 vector, and then we add this to the V2 vector, which is here, and we just take a coefficient 1. And this gives you the vector 0.54. So here might be good, you just pause for a minute and you try to figure out what is this vector, and then you will see what this means, right? You're taking 0.5 of the vector V1, so up to here, and then you're taking 1 of the vector V2, which gets you to this point here, okay? So indeed, you can see 0.54 is here. Okay. Another case that you might want to think about is what happens when the columns of V are dependent. Right, so in this case here, what you can see is that we have V1 is equal to 1, 2, and this is clearly equal to 2 times V2, right, which is equal to, no, excuse me, it's the reverse, right? So what I wanted to say is that we have V1 is equal to 1, 2, V2 is equal to 2, 4, and then we clearly have here that V2 is 2 times V1. So the columns are dependent. And then what happens if you trying to form this sort of linear combination? So things here, again, I take the same coefficients as before. No, actually, it is reversed, but it doesn't really matter so much. What you will see is that if you try to take different sort of combinations, you will get a vector here. So let me write this as VO for the output. VO is always going to be essentially a linear is always going to be a scalar, C, let's say, times the ordinal vector V1. Okay, so it's always going to be this way. You can only create the vector V1, essentially. So in terms of terminology, what we discuss usually when we take these linear combinations, again, of these two vectors, we talk about the column space of these vectors. So we say that when we take all these combination of these columns, this is a so-called column space. It has different names. You can talk about range or image. And of course, analogously, if you were to take linear combinations of rows, you will get the row space. So let's move on to matrices. So what is a matrix? A matrix is simply an extension of a vector where now you have a rectangular array of numbers. So instead of just having one column or one row, you now have, so essentially, as I said, right, a rectangular array. So you have, in this case here, let me write it down. We have a matrix that has from A11 elements up to APD. So these are all the elements of this matrix, right? So we have essentially here one row of the matrix, and we have P rows of the matrix. And then you can see that you have here up to D columns, right? So this is this matrix has dimension here P rows by D columns. As before, you can transpose it. So remember, the transpose operation just means you take here the column and you write it as a row in this matrix. right? So you would do the same as well for the first row. You would transpose it, and that will become here the first column of the matrix A transpose. Another concept is the concept of multiplication. If you give me two matrices, A and B, what is very important here is the dimension. This inner number here, the n, let me highlight this. This n here has too much, okay? And then, so when you do this, when you multiply this matrix A by B, so which I denote here by C, the matrix C here is gonna have dimension M times D. And how do you get one entry of this matrix C? So let's draw a little picture. We have that the matrix C is the matrix A times the matrix B. And now we're asking, we'd like to get, so this is the C matrix, and we'd like to get one entry of the C matrix. So specifically here, we want the ijth entry. So let's say this point here is Cij. So what we have to do is that we have to go over the ith row of the matrix A and multiply this here by the jth column of the matrix B. Okay, so this is the ith row of the matrix A. And here, this is the jth column. And so mathematically, you can just write in this way. So, right, you have to go over all the elements here. And then what did we say? We said that this matrix has dimension m by n. So when you're going across here, you have n elements. And here the same, right? You have n elements. So you're summing over all of these elements. And so here, importantly, in terms of indices, you have, so you're looking at Cij. So you're going to look at the ith row, as I said here. And for the B matrix, you're going to look at the jth column. So you have this j here. Okay. And then here, the k is summing these indices here and here. What are some important properties of this matrix multiplication? So first of all, it follows the so-called distributive property. So that means that if you take three matrices, A, B, C, you can simply write A times B plus C in brackets here as A times B, this one, plus A times C, this. And the same here when you do it for A plus B times C. Then it has a so-called associative property. So you can essentially, again, multiply these three matrices, and it doesn't matter if you first multiply AB or if you first multiply BC. However, what is extremely important is that matrix multiplication is not commutative. So if you do A times B, in general, this is not the same as B times A. This is, for instance, true for diagonal matrices, but in general, it is not true. Let's review the notion of an inverse. So the inverse of a matrix is what we are going to denote with A upper squared minus 1. And this inverse satisfies essentially the fact that A times A minus 1 is equal to A minus times A is equal to the identity. And here I want to attract your attention to the fact that, so this identity matrix, right, which is an n by n matrix, essentially it's, you have you have ones on the diagonals like this, and everywhere else you have zeros. Okay. And this here specifically was defined for a square matrix, so an n by n matrix. There are various notations that I've also added to the lecture notes. Encourage you to look at it. For instance, usually I will write a small bold letter for a column vector. Capital letter bold would be a matrix. Transpose I already discussed. So we will discuss some of these notions a bit later, but if you have, if you want to refer to essentially the notation, there will be a table in the notes that you can look at. Okay, so I concluded here for the first part.